first session of the last session, so we thought that the jet lag would make it easier.
Okay, that's good.
It lasts, but without further ado, David Stoffer is going to be talking about spectral analysis of non-stationary time series.
Okay, thank you. So this is sort of a long. So this is a few ideas that I've had, and so sort of a long story. But this is joint work, I should say, with Ori Rosen, who's in Texas, and Sally Wood in Melbourne. Okay, so so the best place to start is the beginning, right? So the problem started when I had this problem, basically as a genetics problem, and I wanted to do spectral analysis for point processes. So the process xt takes values in, in this indicator sort of vector, and so you observe these over time or over space, and then there's some correlation structure, and you're interested in, basically the cyclic behavior of these things. So in the stationary case, I was able to come up with some satisfactory results. And then moving to the non-stationary case, it was not so easy, so we tried some different things, some sort of segmentation kind of things. And then the problem is it's not very easy, as Ziggy Stardust. I don't know, some of you must know Ziggy Stardust. He says it's not easy. It ain't easy, and it ain't. Okay, so then these nice Bayesians came to my door selling cookies, and I thought, okay, so I'll try some of these nice cookies. And they tasted pretty good, so I ordered more, and so we started working together. And this led to a series of papers. The problem is if you just say, okay, I want to do local spectral analysis for a point process, as Ziggy Stardust says, it ain't easy. And so then you go, okay, well then let's make it, okay, let's take this in pieces. So first we did, okay, how would you do estimation of a multivariate? So this is a multivariate problem. How do you do estimation of a multivariate spectrum? And the point is you can do that unless, so that's an easy problem. Unless you want to smooth different components differently, then that's a hard problem because you have to worry about non-negative definiteness. So we came up with a method there that was this paper here. And then, okay, so now that we know how to do it in the stationary case, how do you do it in a non-stationary or locally stationary case? And that ain't easy. And so we thought, okay, let's just do univariate, sort of, let's think about what we would do if the data were Gaussian-like. And then that's this paper. And then this, I think this has some cute ideas, but generally the cookies aren't very good. And then, so we decided to try a new recipe, and that's this paper. And you see, I'm sort of moving off to the end here. And next one you'll see will be the fourth author, and then fifth author, and then 0. So you notice there's some sort of slight shift there. Okay. So, but the cookies are still good. The cookies are great. So let me, so I'm going to talk about the last two, by the way. This doesn't go backward. Oh, yes, it does. Okay, so I'm basically going to tell you a little bit about these two because they're fun. And so here's sort of a motivating problem. You have this Southern Oscillation Index, which is it's the measure of the pressure difference between Tahiti and Darwin, Australia. And it's a surrogate for the sea surface temperature of the Pacific Ocean. And when it's up, it's cold, La Nina, and when it's down, it's warm. That's why it's red. And these are monthly observations, so you have this sort of annual cycle, warm in the summer, cold in the winter. And then if you filter that out, we filter out the annual stuff, then you see here this El Nino cycle, right? And it's not very regular. It's sort of regular, but not all that regular. It's broadband, like 3 to 7 years. Okay, so lately there's been this problem of a change in the El Nino cycle. Well, is there a change in the El Nino cycle? So that's one of the things I'll focus on. So this is a kind of typical problem. So what you see here, these are the temperature anomalies. So you see this is global warming right here. So these are annual averages, well, deviations from an average. And then the reds are El Ninos and the blues are La Nina. And so if you see from this is 1950, then everything, you see, okay, there's a few El Ninos, or a few La Ninas, and then all of a sudden 1980, like, bam, there's a change. And, well, okay, maybe it wasn't quite like a bam, but something like that. Something sort of happened around here, and then all of a sudden the weather changes and the El Nino cycle has changed. Okay, so there's a change point in here, but I don't know if it was really a bam, but something like that. So the idea is that this is evidence that there's something going on, and so you can use these methods to detect whether something is going on. Okay, so let me talk about, so everything in the local stuff is based on stationary approximations. So this is how you do it in the stationary case. So you have we have a univariate time series with a spectral density that's bounded. Okay, so life is nice. You have some data. You have the periodogram. And you know that for large n, approximately the periodogram is the spectral density times these gamma or chi-squares, basically, or exponentials. And the idea was, I guess this is Grace Waba's idea, although probably everybody had this idea, is that you take the log, right? And you take the logs here and you have a generalized linear model where y is the log of the periodogram, g is the log of the spectral density, and the errors are log chi-squares. Okay, and so Waba decided, okay, why don't we just estimate the y's by smoothing splines, okay? And then you can bake the cookies different ways, use smoothing splines. You can set it up as a common filter and do common smoothing, or you can do this in the Bayesian framework. And the Bayesian framework is this. So to be a good Bayesian, you have to have a likelihood, of course. And what's the likelihood? The Whittle likelihood. Okay, basically you have no choice, right? So you use the Whittle likelihood. That's sort of evident. And then, so what you do, so in the spline setting, what you do is you make the log of, remember G is the log of the spectral density. You write it in a linear term and a nonlinear term. And if you remember from yesterday, somebody was talking about using Gaussian processes, with a kernel. And so that's what happened. That's what's going on here. And so Waba, I guess 1980 it was, used this setup to do the smoothing splines. And in a Bayesian setting, what you do is and for spectral analysis, there's no alpha 1. That's out of the picture because that term is 0 in the expansion. So you have a constant here. So you put a normal prior on that. And then for the nonlinear term, you just make it a linear combination of some basis functions. And so you can use any basis functions you like. The thing is that you're doing spectral analysis, so it has to be nice for spectra, right? So you could use polynomials, things like that. But we found that this is a linear spline prior, that these seem to do well because if you have a peak, like if you get things that are too smooth, it smooths out the peak. So smoothing tends to over-smooth. And the sort of linear, whoops, pressed the wrong thing. Oh, you see all my jokes now. Okay, close your eyes. All right, so I better watch where I put my hand. So, okay, so then you put a prior on the betas. And so you could do this as a state space model, but if you're going to do Markov chain Monte Carlo, you don't want to have to iterate through a state space model and do smoothing and all of that, filtering and smoothing. So this sets it up as a regression. And so you do the usual kind of things. You put a prior on the beta, some normal prior. And this tau you see here is your smoothing parameter, what you typically call lambda in smoothing. And so this is basically Sally's idea from another paper that she had with Martin Tanner, where they do Bayesian spline smoothing, scatter plot smoothing, is you make this uniform, so you don't allow it to get too smooth. Okay, so then you want to sample from the posterior right here, right? So you have your parameters here given the data, and so you want to do Gibbs sampling. The tough part is the regression parameters given the data, and the smoothing parameter looks like this messy thing here. So you use Metropolis Hastings to get that, and then you can sample directly from the so you have a known distribution to sample from here with the tau squared. And so I'll just mention that there's a nice paper by Chowdhury and some other people in 2004, JAZA, where they show under very restrictive conditions that when you do this sampling, the Markov chain Monte Carlo, it converges to the proper posterior uniformly. But there's some restrictions. Basically, it has to be short memory Gaussian. Okay, so short memory, I already said the spectrum was bounded, so that's not a problem. The process has to be Gaussian. Okay, so that's somewhat restrictive. The other thing that's very restrictive is this part is gone. So if you know the smoothing parameter, that is, you don't adapt it to the data, then this process will converge to the proper posterior. So at least you know that, under restrictive conditions, you eventually get the right thing. So that's, partially a good idea, makes you feel good that you're not too off the mark. Okay, so here's a quick example of what this looks like. I don't know if you can see it, but here's so some AR2, I forgot what it is. There's the spectral density right here. So here it's logged and flat and stretched, so you can see it. But it looks like this, so it has a nice peak. And so you see the periodogram values are here. I don't know if you can see the spread. The solid line is the true density, and then the dotted lines are 95% credible intervals. So those are the 95% cutoffs for the posterior distribution. So it works pretty nice, and then it just looks like smoothing. Okay, so now we're going to use this technique in local stationary problems. So what do we mean by locally stationary, right? Okay, so here's one thing. So I think this is a cute idea, but somehow not as satisfactory. So I call this swimming the Thames approach, and I'll show you what I mean by that. So actually, I checked, and people do swim in there, but it's not advised that you do that, or at least you don't drink the water as you're swimming. So one sort of obvious approach is you chop the data up into nice segments. And then in each segment, you assume that you're observing a stationary process. Okay, so that's hopefully approximately right. And okay, then what you want to do is estimate the spectrum in each segment. So the trick here is that it might be that when you're in this thing in the first section, you might be looking at something different, right, than the second section. Maybe you see, well, I'll show you the picture. So what we did is we assumed that the spectral density in any segment is a mixture of some unknown but finite number of spectral densities with these probability weights pi. Okay, so I'll show you how this goes. Okay, so this is a simplified map of London. And basically what you have this. So either you're a loser or you're a winner, right? And so suppose that, so there's two distributions here. Think of this as household wealth. Okay, so you're swimming along the river, and then you decide, oh, I wonder what the wealth distribution, household wealth distribution is here. So you get out of the river, take some data, and you go, oh, these guys are a bunch of losers, okay? So you jump back in, you swim another kilometer or so, get out, and you get some data. Oh, these guys are a bunch of losers, nothing's changing, right? And then you swim some more. Then you get out here, and then, not everybody's a loser. And so what happens as you're sampling from here, you're sort of mixing two distributions, the very rich distribution and the loser distribution, right? Then you swim a little bit more. Now you're in this distribution, and as you move along, as you're swimming, what you're seeing, there's two distributions, but the way you're sampling it, it's sort of mixing. So you have that. So also, what you should do is if you say, okay, there's some finite number of distributions, you might realize that, okay, well, if I'm over here, and this looks the same as it did over here, right? So I use the data from this side to help me estimate what's going on all over the place. So usually when you segment, right, you segment and you go, okay, this is here, then you use the data in this segment to estimate what's going on right here. And then if you see the same thing later on, you don't say, oh, I'll use this data to help me estimate things. So you don't really put it together. Whereas in this setup, we'll use, every time you step out here, we'll use the data to estimate this distribution. So those segments can be small. You don't have to have a long series, to estimate the spectral density. Okay, so, okay, so that's what we meant by locally stationary. So basically, it's how you happen to divide it is how things are stationary. Okay, so then you do what you did before for the stationary case. So you have your generalized linear model, right? But for each segment, and you assume that what you're getting is this mixture of distributions, and then you just do the same thing. So I'll just go through this. You don't need to see it all, but basically what happens is you put a prior on the number of segments, and then this is the other key thing. I'm not sure I like this so much, but we put multinomial, the linear logit probabilities on here. So this is used in mixtures of experts, but I'll show you. I don't know if it's very satisfactory. It's a little too smooth for me. And then you put this, because you're going over different models, you have to do reversible jump Markov chain Monte Carlo. But it's similar to what you do before, only there's a few more ingredients, that there's so many different distributions, and then you have you have the J, and then you have the pi. So it's a little bit more difficult to sample. But I'll show you, here's a quick example. So here you have an AR1 with 0.9, and then it switches to minus 0.9 somewhere in the around 450. So we chop it up into 16 segments of 64 data points. The change is in the 7th segment. And so if you know that there's two components, so this is just to give you an idea of what's going on. So suppose you know there's only two components, like swimming the Thames, then you assume the spectral density has this form, the log spectral density. And these are the probabilities. So you see the mixing probabilities are going like this. This is 0.5 here. So on this side, you're saying, OK, you're coming from this F1 distribution, and on this side, you're coming from F2, because you know there's two. And then you use all the data to to estimate, not just in one segment, but all the data in this segment to estimate F1. I don't know if you can see it, but the dots, the solid lines are the true ones, and the dashed lines would be the estimated densities. Okay, so this is somehow unfulfilling, I guess. The cookies, I don't know, there's not enough baking powder in the cookies. I don't know. I mean, I sort of like the story. It's a fun story, but okay, so somehow not so satisfying. So then we did this, and notice my name. This is when my name gets removed back one. So now they're sort of kicking me out of this. But okay, so in this idea, so the thing is you have to give a name. So people remember names, so we came up with this nice name, AdaptSpect, right? So you can remember that. That's easy to remember, and, right? So, right, you have to give your cookies a good name so people remember. So it's just marketing, right? So we called it AdaptSpect, and this is an adaptive method. And now, if you're going to find, if you're saying, okay, there's change points, then there better be like, bam, change points, right? So if you're looking for points of change, you have to assume that there's change. So we do that. So now we'll assume that we have a piecewise stationary process, and we're looking for the actual points that change. And if it's not true, it's okay, I'll show you. It's sort of, you get the idea that if that's not true, then you'll see that that's not true from the analysis. Okay, so here, this is the timeline, and you assume that there are m sections. There could be, or m segments. If m equals 1, that means that you have one stationary piece here. And then you're trying to find these change points in here. Okay, and then each one has their own spectral density. It's possible that, let's say, the first segment and the third segment have the same. So if you had signal A, then B, then A, then B, that's fine. So you would use all the A's to estimate the A signal still in this setup. Right, you're not just saying using this data to estimate signal A and then use this data to estimate signal A again, right? You would combine those. So there's some finite number of spectral densities. The C's are the points of change, and then within each one you have a periodogram, and we just assume that there's some reasonable space between them. Okay, so now you do the same thing over again. So we're going to use the Whittle likelihood. So in each piece, right? Go back. So in each piece, Whittle likelihood, right? So if you tell me where the change points are, Whittle likelihood, we're going to do the spline smoothing in each one for each different spectrum. So we have to have priors, right? Same as before. And then, given the number of segments, we just made everything uniform. So uniform, the location is uniform, the prior is uniform. And on the number of segments, the prior is also uniform on some large number, M. And we tried that. There are other things, like we tried other priors, Poisson kind of priors and things like that. But this seems to work pretty well. And then there's two problems here. One is where are the endpoints? So basically there's a within model move, and you go through this. It's sort of a long process. You go through this these steps to decide whether where you should locate and things like that. And then there's a between model move, where either you add a segment, you say, okay, there's a segment that should be added, or so P is the proposed, and C is the current. So suppose you have your current is MC, then you either propose to go up or you propose to go down. And because you're going across models, you use reversible jump Markov chain Monte Carlo to do all of this stuff. So it's basically the same kind of thing that you do before local smoothing, but within there you're moving, you're offered to move the points one way or the other, and you're offered to remove a segment or keep it in. So here's an example that sort of demonstrates what's going on and how you can, if the model's not true. So this is the benefits of model averaging, of averaging over models. That it helps you out quite a bit. So here's an AR1, time-varying AR1, and in the blue case, it's not the model. It's changing at every point, right, like this. So that's this is the coefficient. It's going from -0.5 to 0.5. So this is changing very slowly. That's not the model. The green one is the model, where at 250 times 250, it changes from -0.5 to 0.5. Okay, so what happens is you put this into the process, and for the blue series, so remember the blue one is not right, not our model. The green one is our model. What happens is, okay, the modal value of the number of segments is 2 for each of these problems. So I'll show you what happens when you say there's 2. And so what you're seeing here, this histogram here, are these probabilities. The probability that the change point is at time t given the data. And you see for this one, it's all over the place. So it's saying, yeah, there's something going on here, but sometimes you're saying the change point is at 100, sometimes you're saying it's at 200, other times you're saying it's at 400. So it knows something's going on, but it can't really find the place where there's a change. So what happens is, by model averaging, you get this big distribution. So you say, there's not really a change point. It's like all over the place. And then if you look at the cumulative distribution, it sort of looks like what's going on, right? So you see here, this thing's changing all the time. Whereas when there's a fixed point, then here's the histogram, the posterior histogram. It's basically centered right where you want it, and there's a cumulative distribution. So even though it's not correct, you still get a sense that, okay, your model's not correct. It's all over the place, right? And then if it is correct, then you see it. Okay, so maybe then you do something else here. Okay, so here are the spectra. This doesn't look that good. I don't think this is in the paper. This is all I could find. So maybe this part's not in the paper, or maybe we fixed it. I can't remember. There's some end effect here, but this is time. This is frequency with the high frequency right here. So in the beginning, you're high frequency, and then as you move with time, you're in the low frequency. So this is the smooth one, which is not correct. And then this is the change point, which is the model. And you see it gets it pretty well, except these are supposed to be AR1 spectra, and there's a little blip there. So I don't know what that is. Maybe that's why it didn't make it in the paper, or maybe, I can't remember, but it gives you the, now I'm not sure what that little blip is, or if it's very big or not. So I don't know. That could be an artifact of smoothing. I just can't remember, but it looks okay. Like Reiner Dahlhaus said, as long as you don't look at the difference, right? You just show the picture and don't look at the differences, then it looks fine. Okay, so now let's go back to the El Nino Southern Oscillation Index and see whether there's been a change. So think of this as, okay, now we're going to test whether these things are stationary, or if there's been a bam change in 1980, March 3rd, 1980, El Nino decides to change. Okay, so, all right, so here's Southern Oscillation Index. This goes back all the way. So when everybody else is going to their gold rush to become rich, there's some guy going out and measuring the pressure difference between El Nino and between Darwin and Tahiti. So that's, that's a scientist for you, right? We don't care about. So I could just like, where is everybody? Oh, they're gone to get rich, but there's still one guy who's measuring the difference, okay? So let's assume that there was one guy that was doing this. Okay, so 1876, this is the Southern Oscillation Index. I mean, you don't obviously see a change there. Then this one is, oh, the change isn't down there. The change is in the mid-Pacific. So this is another one. This is called Nino 3.4. Don't ask me why it's called that. And I don't know, can you see that very well? So this starts in 1950 because 1950, the gold rush was, I don't know. So, so this is the sort of mid-Pacific Ocean. And then this is just the pressure in Darwin. I guess this is supposed to be some indicator also, not the pressure difference, but just there. It's called DSLPA. I can't remember. I know D is Darwin. That's all I know. Okay, so this is also from 1950. So remember, the story is from 1950, you know, it was one way, and then 1980 it changed to something else. Okay, so we run this, you know, fit this through our model, and in the end, you can get a posterior on the probability of the number of segments given the data. And for the Southern Oscillation Index, I'm 95% sure that there's only one process. Okay, but although there's 5% probability that there's two, that's significant, right? Isn't 0.05 significant? So I mean, if you look at all of these, it's pretty overwhelming that there's no change in Southern Oscillation Index. And I mean, you can't see it. So, you know, but the thing is now when you read news articles, this is taken as a given. And so when we actually published this paper, I got some emails from climate people, and it was sort of like, you know, what the hell are you doing to? Yeah, we found the same thing. So this is controversial, I think. But I don't see it. You know, we don't see it. And so in all of this, by model averaging, and you get rid of you average over all the parameters, then you have this nice sort of test, right? So all the things that you would want, you have an estimate of the spectral densities, you have a test for the number of segments and all of that. So I guess, so one last, we know where you are. Okay, so you know, let's look at something that we know. And so I think this is from a paper that Sally did with Robert Cohn. And basically, it looks like the earthquake data in our book, right? I mean, the explosion data. This is like the typical thing that we start off with. This is what an explosion looks like. And so they sort of got these AR6s, right, that with breaks here. So there's 5 segments, and they made this thing that looks like the explosion. Okay, so then we're going to try and find those, use our methods on this. And okay, so we run it through. This is the number of segments and the posterior probabilities. So it picks five segments most of the time between 0.9 and 0.1. Right, there's the distribution. There's some distribution that there's one more segment, a little bit at 6, maybe a little bit at 4, but nothing else. And then you see there's the posteriors at the points. And there's a red line there. I don't know if you can see it, but it's pretty much, these guys get it. So when we know where you are, we find you. Okay, so finally, I'd like to thank the organizers, John, Paul, George, and Idris, who remind us that all you need is love, as long as you have some breaks. So I think we should take this time to thank them. Thank you, guys. You did a great job. And you guys were a lot younger then, right? It was hard to find such a young picture of you, but you have changed a little bit.
Let's thank David.
Hey, great stuff. Just to clarify, in your last simulated example, actually in Sally's example, when you have these distributions on the probability of, I don't know, here you have like, what is it, 5 segments to the left? So the final time frequency plot, the estimated spectral densities, they are calculated
from averaged over, right? So it would be the posterior mean of all the spectral densities.
Okay.
Yeah, and they would be averaged over, but I mean, basically, it would look like, right? It would look like this one here. You would
Actually, explain this extra, stuff. That
yeah, right. So it's extra step from the probability where you're not, where you miss
it. The maximum. I mean, why not take the majority vote or something like that?
I guess Bayesian's like posterior means the cookies taste better that way. I don't know. No, that's right. You don't have to do that, right? That's the Bayes estimate, isn't it?
What I really find exciting is that you use the Whittle estimator, and I have been, so I'm doing a little bit of spectral estimation in a non-Bayesian way, and I'm also using the Whittle, and I've checked literature and haven't really found very much on that. So I'm very happy to see that. So
really? Oh, I thought. I mean, that sort of seems in this way, right?
Oh, I mean,
it's obvious,
Bayesian,
right?
but in the non-Bayesian context,
right?
I found one reference actually.
Wow.
But somehow it's so one nice thing, for example, if you just write it down as a local Whittle likelihood, you get the usual spectral estimator out of it, and you can see that log spectral estimation is less efficient and all of that. So basically, there comes a lot out of this Whittle thing. My question to you is there even some more general theory in Bayesian context? So would there be something, this is probably a stupid question, would there be something like a conjugate prior which fits to the Whittle in a certain sense or whatsoever? Is there anything on this?
Oh, yeah, no, I think that's the thing, you get into these difficult problems. Even in the, even in the stationary case, you have this problem right here. So even if you're doing this spline smoothing, you have this kind of messy thing. So right, I don't think so. For the smoothing parameter, it's okay, but for if you try and estimate the Gaussian process here, this part, I don't think so. So maybe if you fix something, that was another thing, the Chowdhury paper, right? They have to use a certain kind of they use some kind of polynomials for the basis, and then you have to say, okay, I know this. So you have to make concessions, right? You have to be really restrictive. It has to be Gaussian. It has to be short memory. So maybe if you restrict enough, maybe you could find something.
How quick is this stuff?
Oh, it takes about a year. No. Actually, yeah, it takes a while. But every year it gets faster for some reason. It gets twice as fast every year. So if you wait long enough, it will just come like this. No, I don't know. That's Ori's problem. Let him wait.
Well, if there are no further questions, let's thank David again.